All right, so welcome to this deep dive into some pretty cool AI stuff.
Yeah.
We're going to be looking at the paper Search-R1, Training LLMs to Reason and Leverage Search Engines with Reinforcement Learning.
Nice.
I mean, the title kind of gives it away.
Yeah.
But this is really all about teaching LLMs to use search engines, right? Like to actually go out there on the web,
Right.
find information, and then use that to reason better.
Yeah, it's pretty neat.
And they had some, pretty impressive results.
Yeah, 26% improvement on Quinn, 2.57B, 21% on the 3B version,
Wow.
and even a 10% boost for LMA 3.23D. So that's significant, right? Like this is not just a small incremental thing.
Not at all.
These are big jumps, especially in a field that's moving so fast.
Right.
And they did this all on question answering tasks, right? So like really practical stuff.
Yeah, exactly. I mean, question answering are like the bread and butter of so much of what we do with these LLMs.
Right.
So any improvement there is a big deal.
Yeah, and it's not just about giving them a search bar. It's about integrating that search into the reasoning process itself.
Okay, so how they do that? Like, what's the magic here?
Well, they start by, pointing out some of the issues with the way we've been doing things so far. Like
Okay.
RE, for example, Retrieval-Augmented Generation.
Right. ARG. Yeah, everyone's heard of ARG.
Yeah, it's useful, but it has its limits, right? It can latch onto the wrong info early on.
Yeah, and it's not great for those like multi-step questions where you kind of need to think, search again.
Exactly. It's not very dynamic.
Right.
And then you have the approaches that try to teach LLMs to use search as like a tool.
Right.
But that needs a ton of labeled data to show them when and how to use it.
Yeah, it's like trying to teach a kid to use a hammer by just showing them pictures of hammers being used.
Yeah, exactly. You need that hands-on experience.
Right.
And that's where Search-R1 comes in. It's saying, hey, let's use reinforcement learning. Let the LLM figure out the best way to use search through trial and error.
Okay, so RL, it is, I mean, I guess that makes sense, right?
Yeah.
It's all about learning from experience.
Right.
But how do you even set that up? Like, how do you create an environment where the LLM can learn to search effectively?
Yeah, it's tricky.
And how does it tie into that whole reasoning process, right? Because that's what we're really after.
Exactly. We want them to be able to reason with the information they find, not just regurgitate it.
Right. And then, of course, there's the whole question of how do you reward it? Like, what's the signal that tells it it's doing a good job?
Yeah, those are the core challenges they had to tackle.
So let's break those down one by one. What were the big roadblocks they identified when it comes to applying RL to search and reasoning?
Well, they outlined three main challenges.
Okay.
First, you got the whole issue of integrating a search engine into the RL framework itself.
Right, because search engines are like these external systems, right?
Yeah, they're constantly spitting out new information.
And that could really mess up the RL training if it's not handled carefully.
Exactly. You need to keep things stable. Then the second challenge is enabling this multi-turn back and forth between reasoning and searching.
Okay, so the LLM needs to be able to search, think, search again, think again.
Exactly. It's like a detective gathering clues.
Right, building up that knowledge gradually.
Yeah, most existing methods don't really allow for that kind of dynamic interaction.
Okay, and the third challenge?
The reward function, right? How do you tell the LLM what it's doing well?
Right, because just rewarding croak answers might not be enough. You need to guide the search process itself.
Exactly. You need a signal that encourages the LLM to search effectively and then reason with what it finds.
Okay, so three big challenges: integrating the search engine, enabling that multi-turn search and reasoning, and designing an effective reward function.
That's it in a nutshell.
Okay, so how does Search-R1 actually address these? How do they overcome these hurdles?
Well, they've got three key innovations.
Okay, lay them on me.
First, they actually model the search engine as part of the RL environment itself.
Whoa, okay, so it's not just an add-on, it's baked right into the learning process.
Yeah. Exactly. It's like the LLM is learning to interact with the search engine as part of its world.
So what does that mean practically? Like, how does that work?
Well, it means the LLM's actions aren't just about generating text anymore.
Okay.
It can also choose to make a call to the search engine as an action.
So it's like a whole new action in its repertoire.
Right. And they mentioned that this works with algorithms like PPO and GRPO.
Okay. For our technical folks out there, proximal policy optimization and group relative policy optimization.
Yeah, those are kind of the go-to methods for RL in this space.
Right. And to keep things stable, they've got this cool trick called retrieved token masking. Retrieved token masking.
Yeah, it's pretty clever. We'll get into the details later.
Okay, so search engine as part of the environment.
Yeah.
Check. That's innovation number 2.
Multi-turn retrieval and reasoning.
Ah, yes, that back and forth we were talking about.
Exactly, and they do this using special tokens.
Okay, special tokens, we've seen those before in other LLM stuff.
Right, but here they use them to structure the whole search and reasoning process.
Okay, so what kind of tokens are we talking about?
Well, they've got search and search tokens to mark when the LLM wants to search.
Okay, so it's like saying, hey, I need to look something up.
Exactly. Then the search results get enclosed in information and information tokens.
Okay, so it knows what's coming from the search engine.
Yep, and for its own thinking process, it uses think and think.
So it can kind of compartmentalize its own thoughts.
Right, and then finally the answer gets wrapped in answer and answer.
Okay, so a whole set of tokens to guide the process.
Yeah, it's like giving the LLM a special language for talking to the search engine.
I like it. Very structured, very clear.
Yeah. And that brings us to innovation number 3, the reward function.
Ah, yes. The good old reward function, always crucial.
Yeah. And they kept it surprisingly simple.
Really simple.
Yeah, basically they just check if the final answer matches the correct answer.
Okay, so exact match.
Yep, if it's right, reward of 1, if it's wrong, 0.
And that's it. No fancy stuff.
No fancy stuff. They found that by just focusing on the final answer, the model naturally learned to use the structure and the search engine effectively.
Wow. So the model figured out the rest on its own.
Pretty much, which is a testament to the power of RL.
It really is. Okay, so we've got the high-level overview of the innovations.
Right.
But I think our audience is probably eager to get into some of the nitty-gritty technical details.
I bet they are.
So let's dive into that. Section 3.1 of the paper talks about how they actually formalize this whole reinforcement learning with the search engine thing.
Right.
Can you break that down for us? What's the math behind this?
Sure. So they're still working with that standard RL framework, maximize the expected reward.
Right, the classic RL goal.
But the key difference is how they represent the LLM's policy.
The policy, okay, so in a regular LLM, the policy is all about predicting the next token, right?
Exactly, given some input.
Right.
But in Search-R1, the policy is also influenced by the search engine.
Okay, because the search engine is now part of the environment.
Right. So they denote this as pi subscript theta with parenthesis dot given x semicolon r.
Okay, pi theta dot given x semicolon r.
Yeah, so x is the input, like before,
right,
and r represents the search engine.
Okay, so the policy is conditioned on both the input and the search engine.
Exactly.
And that makes sense, right? Because the LLM's decisions now depend on what it can get from the search engine.
Right.
So it's not just generating text in a vacuum anymore.
Exactly. It's got this extra source of information to consider.
Okay, so they've adapted the policy to account for the search engine.
Yep.
What about the RL algorithms themselves they mentioned using PPO and GRPO?
Yeah, they took those 2 popular policy gradient methods.
Okay, so for our audience, PPO is proximal policy optimization.
Right.
And GRPO is group relative policy optimization.
That's right.
Both are widely used for training agents with policies.
Yeah, and they adapted them to work with this interleaved search and reasoning setup.
Okay, so how did they do that? What were the key changes?
Well, the core ideas of PPO and GRPO stay the same. PPO is all about making small updates to the policy.
So you don't jump around too much and destabilize things.
Exactly. And GRPO compares different responses to figure out what works best.
Okay, but the key adaptation in Search-R1 is how they calculate the objective function.
Right. And that's where the retrieve token masking comes in.
Ah, yes, the famous retrieve token masking.
Right.
Can you remind us again why this masking is so important?
Sure. So during training, the LLM generates some text, right?
Right.
And at some point, it might trigger a search.
Okay.
And the search engine returns a bunch of tokens.
Right, representing those search results.
Yeah, but those retrieve tokens weren't generated by the LLM.
Okay, so they're not really part of the LLM's own decision-making?
Exactly.
Yeah.
They came from an external system.
Right.
Now, if you included those retrieve tokens in the RL loss calculation, you'd be trying to optimize the LLM based on something it didn't actually produce.
Yeah, like blaming the LLM for something the search engine did.
Exactly, and that would mess up the training signal.
Right, because you want the LLM to learn from its own actions, not from random stuff the search engine throws at it.
Right.
So this masking prevents that.
Exactly. It ensures that the RL signal is focused on the LLM's own decisions.
Okay, so how does it work technically? Like, how do you actually mask those tokens?
Well, it's a pretty simple binary mask.
Binary, so just ones and zeros.
Yeah, it's 1 if the token was generated by the LLM.
Okay.
And 0 if it came from the search engine.
Okay, so you just multiply the loss by this mask?
Yeah, essentially. And that zeroes out the loss for any retrieve tokens.
So the LLM doesn't get penalized for those.
Right.
Very clever. And the paper shows the updated PPO objective function.
Yeah, equation 1.
And it includes this indicator function, I of y subscript t, inside the summation.
Right. That's the mask.
And similarly for the GRPO objective function, equation 2, they use I of y subscript I comma t.
Yeah, and they also add the KL divergence term directly to the loss.
Okay, so that's the difference between GRPO and PPO.
Right, PPO usually handles that KL divergence as a separate penalty.
But GRPO just bakes it right into the loss.
Exactly.
And they apply the masking to the KL divergence too.
Yeah, again, to make sure it's focused on the LLM's own contributions.
Okay, so we've got the RL framework with the search engine built in.
Check.
And this loss masking to keep things stable.
Check.
Now let's talk about the actual process of generating text with those multi-turn search engine calls.
Okay.
Algorithm 1 in the paper describes this rollout procedure.
Yeah.
Can you walk us through it step by step?
Sure. So you start with your question or query
Okay.
and your current LLM policy.
Right.
You also have your search engine ready to go.
Of course.
And you set a limit on how many search calls you're allowed.
Okay, the search budget.
Yeah. So you don't get stuck searching forever.
Right.
And then you initialize an empty sequence of text.
The blank canvas.
Exactly. And a counter for the number of searches.
Okay, starting at 0.
Then the LLM starts generating text token by token.
Based on the input and its current policy.
Right. And after each token, the system checks if it sees those special search and search tokens.
Ah, so that's the signal.
Yep. If it sees them, it extracts the query between those tokens
Okay.
and sends it off to the search engine.
Makes the search.
The search engine returns some relevant documents or snippets,
Okay.
and the system takes those results,
Okay.
wraps them in those information and information tokens.
Right, to mark them clearly.
And adds them to the text sequence.
So the LLM sees those results as part of the text it's generating.
Exactly.
And then it continues generating.
Right. Picks up where it left off.
Okay, so it's like a little loop.
Yeah. Generate, check for search, search if needed, add results, generate again.
And when does this loop stop?
Well, it stops when the search budget runs out.
Okay, so you hit that limit,
Or when the LLM generates its final answer.
which is marked by those answer tokens.
Exactly.
So it knows when to stop.
Yep.
Very cool.
Ha.
Nice, clean procedure.
Yeah, it's pretty elegant.
Okay, so the LLM is generating text searching, incorporating results all by itself.
Right, pretty much.
But to get this whole thing started, they must have given it some initial guidance, right?
Yeah, they used a training template.
Okay, a template.
Yeah.
What did that look like?
You can actually see it in table 1 of the paper.
Table 1, right?
It's pretty simple. Basically, it tells the model to first think about the question.
Okay, so use those thing tokens
Yep. And then if it needs more information, it can search.
using the search token.
Right. And the results will be given back in those information tokens.
Okay.
And finally, it should give its answer in the answer tokens.
So a very structured template guiding the overall flow.
Exactly.
But I noticed it's pretty bare bones, right?
Right.
It doesn't tell the model what to think or how to search.
Yeah, they did that on purpose.
Why?
Well, they wanted to see how the model would learn naturally
Okay.
without biasing it too much with specific instructions.
So just give it the structure and let it figure out the rest.
Right. Let the RL do its magic.
I like that approach, very hands-off.
Yeah, it's about seeing what the model can discover on its own.
Okay, so speaking of RL, let's talk about the reward again.
The reward.
They use that rule-based outcome reward based on exact match.
Right.
Can you remind us how that worked?
Sure. So the reward is basically a 1 or a 0.
1 for a correct answer.
Yep. 0 for anything else.
So pretty straightforward.
Yeah, and they specifically chose not to include any rewards for using the structure correctly.
Really? So no extra points for using the think tokens or anything like that?
Nope. They found that the model learned to use the structure anyway, just by trying to get the answer right.
Fascinating. So the structure emerged organically.
Pretty much.
And I also noticed they didn't use any neural reward models.
Yeah, they talked about that in the paper.
Why not? Those are pretty common in other LLM work.
Well, they were concerned about reward hacking.
Yeah. That's always a risk with neural reward models.
Right, the model might find ways to game the system without actually improving.
Yeah, and neural reward models can be pretty complex to train and maintain.
Exactly.
So they decided to keep things simple and robust.
Yep. Simpler is often better, especially in RL.
Absolutely. Okay, so let's get to the fun part, the results.
The result.
They evaluated Search-R1 on 7 different data sets, right?
7, yeah, a good mix of data sets.
What were they, dude?
Well, they had natural questions, trivia QA, and pop QA.
Okay, so those are kind of your general question answering data sets.
Right.
And then they also had some tougher multi-hop question answering data sets.
Yep, those were Hotpot QA2, Wiki Multi-Hop QA Music, and Bamboogle.
Okay, so a good range of difficulty there.
Yeah, testing it on both simpler and more complex tasks.
And they compared Search-R1 against a bunch of baseline methods, right?
Oh yeah, they went all out on the comparisons.
Lay it on me, what kind of baselines are we talking about?
Well, first they looked at methods that don't use any retrieval at all.
Okay, so just the LLM by itself?
Right, like direct prompting and chain of thought reasoning.
Okay.
Then they compared against methods that do use retrieval.
Okay, so ARG would be one of those?
Yep, RAG and also IR-Qatar, which interleaves retrieval with chain of thought. And a previous approach called Search-R1.
Okay, so a good range of retrieval-based methods.
Yeah, and finally they included some fine-tuning-based methods.
Okay, fine-tuning. So actually updating the LLM's parameters.
Right, they had supervised fine-tuning and their own implementation of RL fine-tuning without a search engine.
Okay, so they call that R1.
Yeah.
So a really thorough set of baselines.
Yeah, they really wanted to see how Search-R1 stacked up.
And they tried to keep things as consistent as possible across the different methods, right?
Oh yeah, for a fair comparison.
So can you remind us what LLMs they used, what retriever and all that?
Sure, so they used both base and instruction-tuned versions of Qwen 2.5 3B and 7B.
Okay.
And also LLMA 3.2 3B.
Okay.
For the retriever, they used the E5 model.
E5, okay.
And their knowledge source was Wikipedia from 2018.
2018 Wikipedia, got it.
And they retrieved the top 3 passages for any method that used retrieval.
Okay.
For training, they merged the data from NQ and Hotbot QA.
NQ and Hotbot QA.
And they evaluated on all 7 datasets using exact match as the metric.
The exact match, right?
And they noted that they used instruction-tuned models for the inference baselines, because base models usually don't follow instructions well.
Right, they need a little more guidance.
But for their RL training, they used both base and instruct versions.
Okay, so really thorough across the board.
Yeah, very rigorous.
All right, so let's get to the main results.
Yeah.
What were the big takeaways from Table 2?
Well, the biggest thing is that Search-R1 consistently outperformed all the baselines.
All of them?
All of them across all 3 LLMs.
Wow, that's impressive.
Yeah, and the improvements were significant. We're talking 26% for Qwen 2.57B.
26%.
21% for the 3B version.
Okay.
And even 10% for LLMA 3.23B.
So even on a model that's already pretty good at this stuff,
Exactly.
it still made a noticeable difference.
Yep. And these gains weren't just on the in-domain data sets that were used for training.
So it generalized well to new data sets.
Yeah, which is really important.
Absolutely.
Right.
And how did it compare to their own RL baseline, that R1 model?
Right. So that was the one trained with RL, but without a search engine.
Right. So same training method, but no external knowledge.
Exactly. And as you'd expect, Search-R1 did much better.
Okay. So that really shows the power of adding that search component.
Yeah, it highlights the value of external knowledge.
It makes sense.
And what's also interesting is that Search-R1 worked well for both base and instruction-tuned models.
Okay, so it's not limited to a specific type of LLM.
Right. It seems to be a pretty broadly applicable technique.
And it also worked across different LLM families, right?
Yeah, Qwen 2.5 and LLMA 3.2.
So not tied to a specific architecture.
Nope, which is really promising.
Yeah, because in some areas like math reasoning, RL fine-tuning has only been shown to work with certain models.
Right.
But here it seems much more general.
Yeah, which is great news.
Okay, so the results are definitely impressive.
Very impressive.
But they didn't stop there. They also did some really interesting analysis in Section 5.
Yeah, they dug into a lot of different aspects.
Let's start with the comparison of PPO versus GRPO.
Okay, so they looked at how those 2 RL algorithms performed.
Right, both in terms of training dynamics and final performance.
Yep.
What did they find?
Well, they found that GRPO generally converged faster.
Faster, so it learned quicker.
Yeah, and they think that's because PPO often uses a critic network,
Ah, the critic network.
which takes some time to train before it can really guide the policy.
The GRPO doesn't have that overhead.
Right.
But was GRPO always better?
Not always.
Okay.
It turns out that PPO was more stable.
More stable, so less likely to go haywire.
Exactly, and in one case, GRPO actually experienced a reward collapse.
Reward collapse. Oh.
Yeah, on the instruction-tuned LLMA 3.23B model.
So the reward started going down during training.
Yep, which is not what you want.
Not in model.
But PPO didn't have that issue. It was much more consistent.
Okay, so it sounds like a bit of a trade-off.
Yeah, GRPO might be faster, but PPO is more reliable.
Interest, what about the final performance? Did one algorithm consistently do better?
Well, looking at the results in Table 3, it seems like GRPO had a slight edge.
A slight edge.
Yeah, for both Qwen 2.5 and LLMA 3.2, the best models were the ones trained with GRPO.
Okay, so maybe a bit more upside with GRPO?
Maybe, but PPO is very close behind.
Okay, so both are viable options.
Yeah, it probably depends on the specific setup.
And they also observed that instruction-tuned models generally perform better after Search-R1 training.
Yeah, especially with GRPO.
So instruction tuning still has its benefits.
Definitely.
Okay, so they compared the RL algorithms.
Yep.
They also looked at the difference between using base LLMs versus instruction-tuned LLMs.
Right.
What were the key insights there?
Well, as you might expect, the instruction-tuned models converged faster.
Faster, and they started at a higher performance level.
Exactly.
Which makes sense because they're already pre-trained to follow instructions.
Right.
But here's the interesting part.
What's that?
The final performance of the base and instruct models was often very similar.
Really? So the base models caught up?
Yeah.
Yeah.
Which suggests that RL is powerful enough to bridge that gap.
That's cool.
Yeah, it means you don't necessarily need a super fancy instruction-tuned model to get good results.
Right. You can train a base model with Search-R1 and still achieve a high level of performance.
Very cool, very encouraging.
Yeah, it democratizes things a bit.
Absolutely. Okay. And they also did that analysis of response length during training.
Oh, yeah, figure 4A.
What was going on there?
So they looked at how the average response length changed as the LLM 3.23b base model was trained on NQ,
Okay.
and they saw this interesting 3-stage trend.
3 stages.
Yeah, so in the early stage, the response length actually decreased.
Decreased. So it was learning to be more concise.
Yeah, and the reward went up a little.
Okay, so good sign.
Then in the mid stage, both the response length and the reward increased significantly.
Okay, so it was starting to use the search engine more.
Exactly, and incorporating those longer retrieved passages.
Makes sense.
And finally, in the late stage, the response length stabilized while the reward kept improving.
Okay, so it found a good balance between conciseness and using external information.
Exactly.
Very cool.
Yeah.
A nice illustration of the learning process.
Yeah, it's figuring out how to use the search engine effectively without getting too verbose.
Right.
And then they did that ablation study to see how important the retrieved token loss masking was.
Ah, yes, the crucial ablation study.
Gotta make sure it's actually doing something.
Exactly. So what do they find?
Well, they found that the masking was absolutely essential.
Essential.
Yeah, when they trained without it, the training was much less stable.
Less stable.
And the performance was worse across all the data sets.
Okay, so that masking really makes a big difference.
Huge difference. It keeps the training focused on the LLM's own actions.
Right, and prevents it from learning from those random search results.
Exactly.
Okay, so a critical component of the framework.
For sure.
And finally, they included some nice case studies in section 5.5.
The case studies.
Yeah, to give some qualitative examples of how Search-R1 works. What were some of the key takeaways there?
Well, one interesting example was comparing Quen 2.57b trained with Search-R1 against the same model trained with RL, but without search.
Okay, so R1 versus Search-R1.
Exactly. And the question was about a fragrance.
The fragrance.
Yeah, and they wanted to know where the creator of that fragrance was born.
Okay.
So the R1 model without search got it wrong.
It didn't know the answer.
It made a wrong guess based on its internal knowledge.
Okay.
But the Search-R1 model was able to figure it out.
How?
Well, it first searched for the fragrance itself, identified the correct creator, and then did another search specifically for the creator's birthplace.
So it used multiple searches to get the answer.
Exactly. And that's the power of that interleaved reasoning and retrieval.
It could identify its knowledge gaps and fill them in?
Yep.
Very cool. And were there any other interesting behaviors they observed?
Yeah, they also noticed that Search-R1 sometimes did self-verification.
Self-verification. What's that?
So even after it found the answer, it would do another search to double check.
Like it was fact-checking itself.
Exactly.
And they think this is because the RL training encourages that kind of behavior.
Yeah, it's learning to be more confident in its answers.
Makes sense.
So RL isn't just teaching it how to search, it's also teaching it to be a better reasoner.
Very cool. So it's not just about the knowledge, it's about the process.
Exactly.
So to wrap things up, this deep dive into Search-R1 has shown us a really impressive new framework.
Yeah, it's pretty groundbreaking.
It allows LLMs to use search engines effectively to improve their reasoning.
Right.
And it addresses those key challenges we talked about.
Integrating search, multi-turn search, and reasoning, designing a good reward function.
Yep. And the results speak for themselves. Those performance gains are significant.
And the analysis they did provides a lot of valuable insights.
Yeah.
Things like the choice of RL algorithm, the role of instruction tuning the importance of that loss masking.
It's a really well-rounded piece of work.
Yeah.
And it opens up a lot of exciting possibilities for the future.
For sure.
Like how can we develop even more sophisticated search strategies.
Right.
Can we get LLMs to adapt their search based on their confidence?
Interesting.
And what about integrating other types of information sources beyond web search?
Yeah, like databases or knowledge graphs.
Yes, exactly.
Yeah, it'd be really cool.
And it all ties into this bigger question of how do we create truly intelligent AI agents?
Agents that can navigate the real world.
Right, they can learn and adapt and make decisions in complex environments.
Yeah, that's the ultimate goal.
And Search-R1 feels like a step in that direction.
A big step.
So for our audience who wants to dig deeper into the technical details, the code and model checkpoints are all available online.
Yeah, the link is in the paper.
We highly encourage you to check it out.
Definitely.
And let us know what you think.
Yeah, we'd love to hear your thoughts.
Okay, that's it for this deep dive.
Thanks for joining us.
See you next time.